Hello, testing. Hello, testing. All right. Good afternoon, everyone. All right. Good afternoon. It's about time now. Good afternoon. I guess all of you are stuck at home at the moment during this total or partial lockdown in the city of living at this current pandemic situations. So by attending this MIDAS seminar, it's definitely a good choice for you to kill time. So today, I'm going to present it on the Girder span bridge designs, part one, the engineering portions. First of all, I would like to introduce myself. My name is Chong Williams, and I am principal engineer of my own firm, Jutra Bintang Senari PLT. We're based in Kuching, Sarawak, east of Malaysia. I have been in the industry about 16 years, mostly deal with the bridge engineering design. And below can see those projects I've been involved recently. First one, the Batam Tatao Balance Cantilever Bridge, total span of 486 meters long. Some flyover viaducts, trumpet interchange, 85 meters long semi-underground bridges. And a year ago, I've been involved in IC, the independent checking engineer, or the AC in Singapore, on two bridges as well, the Yishun Avenue, and also the other one is Punggol Central West Bridge. So it's a great pleasure for me to MIDAS invite me to become speakers of today's, and I really appreciate that. As we know, engineering life is all about how to achieve efficiency and also the effectiveness. So nowadays, engineers mostly rely on sophisticated computer software to perform the analytical computations by solving complicated metrics and converge thousands or millions of iterations. In addition, there are also many structured software available in the market now, which is capable of carrying the structural analysis, but also equally capable of carrying on the engineering design function as well. And in accordance to many design codes of practice worldwide. And MIDAS, as we know, is one of the leading players in the race. Girder span bridge is one of the most common structured bridge types, can be found not only in Malaysia, but also globally, mainly because of its complexity, its simplicity, flexibility, and also practicality in terms of design as well as construction. In Malaysia, and particularly in Sarawak context, the girder span bridge are made of precast, prestressed concrete girders, and also the reinforced concrete beams. These are the predominant type that are preferred by our local government agency, especially the public works departments, or we call it JKR in local context. So let's get started now. So the part one will be on the engineering, divided into three subparts. The first subpart of 1.1 is on the overview design on the girder span bridge, whereby we will discuss more on the general concept of the design, the bridge components, the deck cross-section elements, and so on, perhaps on the bridge articulations and some sharing of the real-life example photos. Second part of 1.2 we will be discussing how to facilitate the bridge modeling by using the PSC composite wizards that are available in the MIDAS table. And the final part of subpart 1.3, we will discuss on the bridge traffic loading applications and some explanations in accordance to the relevant design code. So let's start on sub 1.1. Well, generally in Malaysia, particularly in Sarawak, the most popular bridge class is the JKR R5 standard class. It either comes in single or dual carriageway configurations. So this type of bridge has been adopted in states' current mega infrastructure projects such as the Penang Highway, Second Trunk Road, the Coastal Highway, as well as the other state roads. So this bridge class will bear the same or compatible driveway constructions geometry with the ATJ R5 road standards as well. So let's talk about deck elements. Usually consists of the carriageway, marginal streets, the footpath, parapets, and also the utility slab. As you can see from this diagram below, the overall deck width will range from 12.4 meters or to 12.9 meters. The variations come in the footpath width from 1.25 meters to 1.5 meters. The length of the span is very much depends on the standards precast girders length that's available in the market. This comes in the standard length of 12 meters, 16 meters, 20 meters, 25, 30, 35, and also maximum 40 meters. The superstructure will consist of RC beam for short span bridge and PSC eye girders also for the 16 to 35 meters long. And if we need to go up to 40 meters, we need to use the PSC girders. Mostly the girders are simply supported, sitting on the either elastomeric bearings or the mechanical bearing type. Link slab will be provided at the pier, at the top of the piers to omit the extension joint over the piers, so give a smooth ride to the road user. So these are the standard PSC girder that's commonly used in the market. For shorter span of 12 meters and below, normally RC beam is used with a dimension of 500 mm width and 1.2 depth in overall depth. So for span length from 16 meters to 35 meters, the PSC eye girders is commonly being used with a depth range from 1.475 meters to 1.98 meters in depth. So we need to go further to up to 40 meters. We might need to use the super T girders with the T flanges on top and with a depth of 2.4 meters. Prestressed concrete grades are usually grade 50s, but in some area where grade 50 cannot be achieved, minimum grade 45 is necessary. Girder spacing will vary depending on the overall deck width and also every designer preference, typically ranging from 1.5 meters to 2 meters. The topping concrete slab typically in between 180 millimeter sticks to 200 millimeter sticks, and usually we adopt the same grade as girders because just to simplify the design and also much better durability. When we talk about PSC girders, we cannot run away from precision. So these are precision data that we need to discuss over here. So the common choice of the wire strands typically two groups. The first one will be smaller diameters, 12.9 millimeters diameters, and the bigger one will be 15.24 millimeter diameters. Both are made of super grade silicon wires, loft relaxations, and stress relief strands. So these are the typical processing design assumptions that the designer used to make during the design. So in order to optimize the processing design, we usually specify 75% breaking stress. Modulus of elasticity stick to 195 gigapascal. 6 nm as drawing figures. Coefficient of friction we usually use from 0.2 to 0.25, and the overall factor also considered from 0.02 to 0.0033 per meters. So you look at the right figures over here, actually show typical arrangements of how we put it, the strength commonly in the English. Next, we move on to the bridge substructure. The bridge substructure typically consists of two types. The one is the piers, in case you have multiple span bridge, and the abutments is a structure supporting the girders from both ends of bridge. The pier will consist of pier headstock, somebody called pier ends in other countries, and of course you can run with pier columns and also bulkheads. The pier headstock usually come in rectangular shapes with constant, even, or with tapered deck sections. Pier column also come in, sometimes we use single wall column, or it can be multiple column in circular or semicircular or rectangular shape as well. And the bulkhead is usually as rigid, thick sections come in rectangular shapes, square shape, hexagons, or any other shapes that depending on power arrangements. While the abutment is a reinforced concrete structure with steel beams, actually the bulkhead, the back wall to retain its backstory, wing wall, curtain wall, and also the transition slab has been placed in order to get rid of any differential settlement behind the abutments. Mostly the abutment types are spill-through type, is bank seat type with a stocky wall, and another one is a much higher wall, which is called the cantilever wall type. So these are the figures or the example of the bridge substructure components. Next, we move to some interesting real-life photos that I've been involved in the recent years. The first one is the Batang Tatau approach spans. As you can see, it's a typical pier headstock with the rectangular shapes and a constant depth, supported by twin semicircular pier columns. You can see the diaphragms and also the girders. So this is the another one examples. This is the flyway viaducts in the city. We are using a single wall type columns with tapered depth of the pier headstocks and also the curtain wall. And this is the completed single span bridge 35 meters featuring the spill-through type of abutments you can see from here. So next let's discuss on how can we facilitate the bridge modeling using the PSD composite bridge results, which is available in the MIDAS civil. So to have a better illustrations of the process, let's take a case study of two span bridge, 30 meters and plus 30 meters multiple prestressed girder span bridge as shown in the below here. So this example of bridge will have the following features, which are very common to be found on a typical concrete bridge in Sarawak. So I can see the span configurations is 29.8 meters, 29.8 meters. The distance is measured from substructure center lines, the abutment center line to the pier center line to be 29.8 meters. As far as the bridge articulation is concerned, the longitudinal translational movement, which is running parallel to the bridge directions, these directions, is to be provided only restraints and pier, while it has been set free in the both abutments. So this type of arrangement actually has the advantage to minimize the forces induced by the creep and shrinkages into the abutment foundations, which is not necessary. So if we don't develop any restraint at the both abutments and lets the girders to contract freely towards the center line of the piers, so there will be minimal lateral forces being transferred to the abutments. So this actually a very good bridge articulation. So the other elements that we're talking about is the carriageway width. It's total 9 meters, consists of two numbers of 3.5 meter traffic lanes, and also remember to add in the marginal strip of 1 meter and both sides of the carriageway. There are two numbers of footpath, 1.25 meters each of them. And the superstructure will be supported by 7 numbers of type 30G PSC girders, measuring 1.83 meters in depth, and to be spaced as 1.84 meters center to center. This made up the overall deck width is 12.4 meters, and the pier column height was just for the insert we picked 5 meters. So then let's look at these elevation developments, elevation of piers, and sectional at pier center lines. Try to remember all these figures because we're going to use these figures to input the field in the composite wizard later on. 1.84 meters center to center, 12.4 meters overall deck width, 5 meters tall pier columns, 7 meters apart of them, and the gap between the end face of the girders to be 200. You can see from here, 100 mm from the face of the girders to the center line of the piers, and the pier column to be 2.5 meters deep. Next, we just move straight to the composite wizards. So when you open up the Prestressed PSC composite wizard, typically this design form will pop up. Consists of 5 tags: layout, sections, tenants, loads, and construction stages. So first of all, look at the layout. So we need to tell layout is actually for us to input or define the geometrical dimension of the bridge. So first we need to choose the precast girder type, and we input the span information as 2 numbers of 30.1 meters span information. Now why we added 100 mm to the 30 meters? Because this is to define the distance from the girder end face to the pier center line, which is equal to 30 plus 0.1 meters, 30.1 meters. So next we define the deck width, 12.4 meters. You can see spacing A and spacing B. Oh, now what is spacing A? Spacing A is actually the gap between the girders and face on top of the piers, which is 200 mm in our case. Spacing B is actually the girder and face to the bearing center line. So in this case, it's 300 mm. So next, we need to define the articulation of the bridge that I mentioned before. So we set free and departments. So we just input a 0 to denote the free in the free movement in the global X directions. And as for the pier, we need to define artificial figures or very large figures, which is equal to 1 million over here. We denote fixity in terms of the movement. So next we define the elastic link length, which is representing the bearing thickness, the plane thickness, and also the girders bottom plate. I'll explain how to get these figures later on. So next we just define the fixity of pier supports as a fixed or subsidi, and define piers. Pier height be 5 meters. The spacing, the part is 7 meters from the between the piers column. Yeah. So after we finish define the layout, we move to sections. Section is where we define the section properties for each of the bridge components. First of all, we tell the software the thickness to be 0.2 meters. And before we can use this composite wizard, we need to define the materials. And the grade 50 concrete has been predefined before we execute the wizard. So we just assign them correctly to each of the components, to the deck, to the girders, and to the diaphragms. Next, we need to define the girders. There are 7 numbers of girders, and spaced at 1.84 meters center to center. So we need to define the girder offset correctly over here, this field. Next, we go to define the diaphragm. So we click on the advanced head over here, it can tell you input which type of diaphragm that you need to model. And in our case, we don't have any intermediate diaphragm. We only have ends diaphragms, one at the abutments and also at the piers. So we just take the relevant end supports and pier supports. And also, we have to predefine the diaphragm sections. So we just assign it correctly. Next, we'll move on to define the girder sections. Now, in post-tension girders, we usually have 2 different sections along the line. One is the typical I section in the meters, and also the other one will be the end block section, both end of the girders. So we need to define it correctly in MIDAS civil as well. So the first 2.5 meters in the other side, 2.5 meters will be assigned to composite and block sections, which also have a predefined in the first place, and left the middle section to be composite I sections. So after we've done the section, we move on to tendons. Okay, we are using a post tensions with a parabolic profile. So over here we have to choose the curve types and we choose appropriate tendon properties, assign the correct numbers of it, and define the profile through the dimension of D, H1, and H2 to be consistent with the drawings that we've shown over here. And I mentioned before, in order to optimize the Christian design, we have to stretch it to 75% of the UTS, which is equal to approximately 1,400 MPa. And then next step, I will show you how to define the tendon properties over here. So this is how we define the tendon properties. First, we choose the internal post tensions type of tendon, and also we define the numbers of strands. In our case, we have 19 numbers of 15.2 millimeters diameters. When you click in the number of strands, the total area will be automatically calculated by the software. It's equal to 2,660 millimeters squared. And we need to tell the software what is the duct diameters. The MIDAS receiver define the duct diameter as the outer diameter. So this is very important to remember. Next, we need to define the crib models. Now we're talking about the crib models. MIDAS receiver actually, it does not build in the crib model as per BS 5400 Part 4 Appendix C, which we usually adopt in the practice. But however, we can choose to adopt this CEB FIP 9090 version, because this version will simulate the crib behavior and will produce the closer match to the figures produced by Appendix C in terms of the total crib strength and also the coefficient. So as an alternative, we should choose the crib models of CEB FIP 1990 version. Yeah. And then the rest of the field, we just have to key in the relevant figures, UTS, the coefficient factors, the over factors, the draw in, and we select bond type because we're going to grout the tendons right after processing. So this is about tendons. So now we are looking at the loading tab. So when we're looking at the loading tab, which is where we define the permanent loading components to the structure. Now first we have to define the deck cross-sections elements, whereby the MIDAS receiver will allow us to define through dimension B1, B2, B3, B4, and B5. So B1, B5 is used to denote the concrete parapet dimensions. The B3 will denote the medians for door carriageway width, and B4 and B2 and B4, sorry, is to define the carriageway. Well, this default setting is not quite consistent of our case study today, because it cannot define the footpath, as you can see. Yeah, and also we don't have the median. So we have to more manually add in the footpath and the curb width after we generate the model by using another separate load cases. You can just go and SDL manually. Afterward, we have to do it. And at the same time, we have to make sure that the summations of B1 to B5 will equals to the overall deck width. In our case, we 12.4 meters. Otherwise, the error message pops up saying that summation of B1 to B5 will not equals to the overall deck width that we defined previously. So by doing so, we have to include the footpath width in our case into the B2 and B4 dimensions. So it make up to be 5.75 meters for B2 and B4. So as we define the way the loading to be distributed throughout the construction stage, typically we have to adopt the first one, separate to be distributed equally only during the non-composite stage. whereby after the topping of the slab is flattened, and so as the composite action kicks in, we just let the loading to be distributed across according to each girder stiffness. So we untick the rates. We only tick the first one before composite. So meanwhile, we have to define the loading, the dead weight, before and after the composite as well. So firstly, we define the concrete density and slab thickness for the wet concrete during the non-composite. And after the composite action kicks in, we define the superimposed dead load for the parapets as well as the wearing surfaces. Again, so by default, the wearing surface weight will be applied throughout the dimension of B2 and B4 area. And again, it's not quite right in our case. So we just need to trim it down manually afterwards to be within the path curve later on. So after the generation of the model. Again, over here, usually we did not consider the utilities in the wizard because simply because the software only allows us to input the utility on single side of the bridge, whereby in our case, we normally apply it at both sides. So furthermore, the location of P1s cannot be specified outside the dead width as a cantilever. So whereby our utility set is actually located outside the dead width. So in this particular case, I just choose to input the utility loading manually afterwards. So I just choose to check off this utility step. So the last step will be on the construction stage. So by default, these are the values and durations and that are being created by MIDAS, and we can actually alter the duration, the member edges after the generation of the model. So we check off the reinforcement as the analysis will be based on cross section instead of transform sections. So design of members are to be done outside the MIDAS because the MIDAS has not incorporated PS 5400 Part 4 into the design module. But the good news is I think the MIDAS has planned to incorporate PS 5400 into the design options. And in fact, that move has been conceived quite some time ago. So I think let's hope we make our life much easier in the future so we can design within MIDAS. So after done all, remember to save it to a template file, and so that it can be recalled to modify or generate new models in the future. So after you click to execute, then here we go. The within seconds, the 3D model will be created after you press the buttons. But like I said, nothing is perfect because before you arrive to this stage, you still need to do some kind of minor modification to the models, like been highlighted here, 1, 2, and 3. The first one will be the end diagram. Second one will be the pockets, and the third one will be on the link slab portion. I will explain one by one. Let's go to the first one. So first of all, we need to, after the generation of the model, and by default, the end diagram will be assigned to the very edge of the girder. It's not in our case. In our case, our diagram will coincide to the center line of the bearing. So we need to move the members on the diagram to be located 300 mm from the edge of the girder. So by simply doing that, we have to go to the nodes and menu elements and choose translate and move it to the correct places. And second, we need to add in the pocket members as well. By default, the wizard will only model up to the pier columns with the supports have been assigned at the bottom of the columns. So in our case, we have to combine pocket. So we need to add in the pockets. And after you have added the new members of the pockets, then we need to connect it to the pier column that has been defined previously by using a master and slave widget links. So after done that, we need to add in the fixed supports at the base of the pocket, where you have to remove the two support has been defined previously by the software. So that's on the pockets. So next we move on the piers. So if you look at it here, the link set actually is connecting the span 1 and the span 2. So the actual thickness of the link set will be 20 mm thinner compared to the link set over here, which is 0.18 meters. So we need to change the link set thickness to 0.18 meters. The link set is separated by 20 mm of expanded polystyrene filler. Just it just act to the bond between the slab and the diaphragm, because this is to simulate the pure surface bond effect of girders. So with the bonding in place, the girders can rotate freely. So no negative bending moments will be developed within the link slab. So this is elastic link height that I mentioned earlier on. How do we get to 125 mm? In our case, the top plate thickness is 32 mm, the bearing thickness is 75 mm, motor plate is 35 mm, and the resist depth is 20 mm. So it's add up to be 125 mm. So we define the elastic link, which is representing the bearing, basically to be 125 mm. So how do we define the fixity to the bearings? Like I mentioned before, we have to use a very large number. We have to use a very large value, say 1 million. It's used to simulate the fixed or rigid conditions, while the null value is to simulate free and sliding conditions. So it's very clear over here. So now, apart from the geometrical modification, we still need to do some minor tweak on the composite section as well. Because by default, the null value has been assigned to both the element 1, which is the girders, and also the element 2, which is topping slab. The edge in forms of the days shall be input in both elements, or the analysis will be brought. So typically 7 days is to be assigned to the girders, and 3 days is to be assigned to the topping slab. Now this edge in days is in fact represent the edge of the concrete structure before it starts to receive any external loadings. So these factors play a very vital role in the calculation of the creep strength of the concrete, especially for the prestressed structure. So now we move on to the next. On how do we use the prestressed composite from an existing model file? So how do we reuse the composite wizard file to create another village model in the fastest possible way? So all engineers emphasize on the effectiveness and efficiency in producing the quality design work so well. There are 2 ways. First, we modify from the existing village model, whereby it has been tested and proven to work flawlessly. Well, the second way is just start from scratch, open a new file. So if you choose to modify from existing model file, first you have to delete all the nodes, frame elements, and plate elements being created in the existing model file. Then you have to delete all the groups, structure, boundary, loads, and standard groups. And you delete the first 5 static load cases in the CS stage, which is safe weight, concrete, barrier, wearing surface, and pre-stress. Then you also have to delete all the boundary conditions defined, support, elastic link, rigid link, everything. Then delete all the construction stages, all the composite section, and you have to delete, last but not least, the dummy section and the material sections. So after you've done so, you can just load the prestressing composite file again and open up the wizard file. For example, in our case, we will H2 span 30 to 30 wizards, and you modify the items within the wizard file to suit the new bridge modeling. Or you can choose to start from scratch, just opening a new file, new fresh file, and then you start to import the section properties and the material properties and the loading combination cases from an existing model file into the new file, and then to do the same thing again. Now, the advantage of using the existing model file and the wizard to create a new model is that you do not need to recreate the material and section property because you already predefined in the first place. And the second thing, you do not need to recreate the loading combination case, which could be proven to be very, very tedious and hassle effort to create loading combinations. So in the sense, you save time, save effort, and also reduce mistake when you're starting from scratch. So I hope all you get it. Now we move on to the last portions, which is the bridge traffic loading explanation and applications. So currently, there are only few Southeast Asian countries, including Brunei, Singapore, well, previously, and Malaysia, of course, are practicing British standard as a primary design standard for bridges. So, however, Singapore is the first one to fully migrate to the Euro code since I think it's 2014. So, as for Malaysia, the intention of the migrations and the preparation of the relevant national annex to Euro code had been consent since many years back as well, but until now we're still not ready to fully migrate into the Euro code nationwide, especially EC2 for the bridge design. Hence, we are still very much depending on the bridge standards, which is the BS5400 for the bridge design and the BD3701 with the BS5400 Part 2 as its Appendix A for traffic loading definitions. Apart from that, Malaysia also practiced the JK Malaysia specific bridge Liveload for bridge, which those bridge lie along the certain routes, especially the federal routes, which is involving the LTAL, long-term axle load policies, and also the SB20 units, which can be up to 450 tons. But this is not a common case. Since this is not common and practiced beyond Malaysia, so it will not be covered in our topic today. So the standard and design criteria that we have been picked to be covered by today is actually, like I mentioned before, the UK Department of Transport BD3701 lots for highway bridges, the JKR specification for bridge Liveload, which is not covered by today, and the traffic loading criteria were made up of HA loading alone. It can be a combination between the HA and HB loading. The HB could be guided on the center line of the carriageway or to be unguided on the carriageway, depending on the agency policy. And the JKR Liveload consists of LTAL loadings and a special vehicle SB20, which is not to be discussed over here because it's not applicable to other countries than Malaysia. And we talk about the design criteria. So the design criteria is actually depending on the loading combination type, the limit state design, and also the class that we are looking at, the design requirement, and also the combination of the Liveload. For example, if we're looking at a prestressing structure, in our case, the 30G girders. So we're looking at the loading combination type 1s, and at the serviceability limit states, we have to design the girders to meet the class 1 requirement as being required by the BS5400 Part 4, whereby the decompression requirement has to be met, which is no tensions to be developed along the section of the prestressed girders. And the loading to be considered either HA alone or the combination between the HA and the HA30 units. So the similar criteria, as you can see, is applied to the type 2 to 5 combinations, and the design will be based on the class 2 and 3, where it allowed to take tension, but within the allowable tension of the concrete. And the loading to be considered is HA plus HB45 unit as well. And the same thing applies to the other type of the combination and also the other type of structure as well. Due to a time constraint, I'm not going to explain one by one, as you can study within this table. Now we move on to how do we define the carriageway and notional lanes to the BD37s. Take for instance, in our cases, the carriageway width, actually the width between the race curves, our case will be 9 meters from the footpath curve to the footpath curve, the other sides. So 9 meters. And according to the BD37, we fall into this group. Above the carriageway width lies between 7.5 meters and 10.95 meters. The number of notional lane that we should consider is 3 numbers. So the each notional lane will be 3 meters individually. So now let's look how can we use the MIDAS table to apply those traffic light roads. First of all, we need to define the length. For example, we need to define the first length, we call it length 1. And then the length width is 3 meters. Eccentricity is 3.2 meters from the reference line that we set. And the wheel spacing is actually 1 meter. Consider. For the pedestrian, we need to define the length for the pedestrian as well. Look at it, we define 1.25 meters for the length width. And this is the position representing the eccentricity. The wheel spacing we set to 0.456. Actually, what is the wheel spacing? The wheel spacing actually is the distance between the wheel load in one single axle cross. So by default, MIDAS sets 4 wheels within one notional length. So we just need to define equally the wheel spacing between the 4 wheels. So in this case, 1.25 divided by 3, not 4 actually, 3 space, because you have 4 wheels, so we have 3 spaces. So equal to 0.416. So for example, the HA length is 3 meters, so we divided by 3, we become 1 meter each. So after you define all the traffic length, you can always choose to display the length as being defined correctly. So the green dot actually represents the wheel load positions according to the wheel spacing that we specify. And the length name text over here, they're actually representing the center line of the specified length. So you can check every time you have defined the length, so make sure the length is being defined correctly. Next, we move on to how do we define the vehicles. So first, we need to create the HA loading vehicle. We choose standard HA loading. And when HA defined, the MIDAS will automatically adopt the different loaded length with a different loading intensity. So you also apply the length computations and also the loading pattern to produce the most severe loading effects on certain members that are currently under your interest. So something goes to the HA and HB auto. So the MIDAS will automatically adopt different HB configurations and also the HA plus HB loaded length commutations and also the loading pattern to produce the most critical loading effect to the structures. So you can choose how many numbers of units for the HB you are designing to. You can choose HB 30 units or HB 45 units. So next, we define the pedestrian loading definition also. When pedestrian is defined, the MIDAS will also assign pedestrian loading in accordance to the appropriate loaded length and intensity to produce the most critical effect to the structure as well. So remember, pedestrian loading is to be combined with HA moving cases and also to be combined with HA and HB moving cases. But it do not need to be combined with SB if I consider SB20 in the design. So next we move on how to define the moving cases, we call it. So we need to define the HA moving cases, whereby the HA UDL plus the KL loading is involved. So remember, we have to untick the outdoor Liveload combinations because HA is not available in the outdoor Liveload combinations. So we have to untick it before we can able to select the subload case before we can select the HA vehicle over here. So we create the subload case and then we selected the number of loaded length to be 3 numbers. In our case, it's three notional lengths. So we select the HA vehicle loads and we assign appropriately the length that we defined previously, length 1, 2, and 3. And then click OK, then it will be defined. The HA UDL moving case will be defined. Next, we have to define the HA plus HB45 outer load cases. Now, in this case, we need to take the outer load connection because in order to use the HA and HB auto functions within MIDAS. So once we take the auto Liveload combination, we can choose actually the one that moving load case to be created to the severely limit state or the ultimate limit states. And also we can choose which combination type that we intended that moving case to be. We can choose combination 1 or combination 2 or 3. So by doing so, the software will automatically assign the HA and HB combination according to one of these figures specified in the BD37. Either the HB will be lying wholly within one notional length, or we can be choose to straddling between two notional lengths as been shown in the figures here. So next we need to define the pedestrian moving as well. So same thing, we have to choose the vehicle type as pedestrian, and then we assign the pedestrian lane accordingly. Now next, this is a table showing the load combination for traffic loads that we use typically for our design. So usually we need to correct the HA HA loading at the service delivery limit states for the load combination type 1. So the loading component that involved will be HA-UDL plus the KL, also to be combined with the pedestrians. So the loading factor is all as per the BD3701. So you can study the tables. I'm not going to explain one by one due to time constraints. So next we move on to the how do we generate the loading combination by using the auto generation functions, which is available in MIDAS. So this is quite a new features actually, because I believe the DS5400 loading combination type has been added into the software recently. I think last year. Previously, we are not able to do so. So we tried how do we make use of this auto generation function to correct the loading combination in split seconds. So first of all, choose the concrete, and then we choose the appropriate design code, which is 5400 over here. Then you can choose the bridge type to be roadway in our cases. And then in order to correct the HA loading combinations, because HA is not the auto moving cases, so if we choose the HA-UDL, we have to choose the vehicle type for the software to apply the relevant partial load factors. So when we choose HA-UDL, the BS vehicle type will comes up to be like this. And then you just click on the BS vehicle partial load factor tables, it appears like this. It's for you to choose which vehicle that you want the software to apply relevant partial load factor to you into your moving cases. So for HA, for instance, we have to choose HA. So over here, we just choose HA load. And then by clicking X, afterward, we have to choose the partial load factor for the inaccurate load effect, which is usually is known as the gamma F3. So by default, the value has been set to 1.1. So afterwards, you just click OK, and then the software will generate the load combination involving HA-UDL for you. And while we need to define HA and HB auto, the same process goes on. But this time, when you choose the HA and HB auto, then you are not able to choose the BS vehicle type because the software will automatically apply the relevant partial load factor into the HA and HB45 auto cases. Same thing goes to the gamma F3. So these are the once you select the OK, and then the appearance will appear like this. The loading combination you can see has been created for you for the ULS combo type and the SMS combo type 1. So over here. So this I have to remind the user is that when you look at try to examine the load factors of HA-UDL, over here is shown 1.65 actually consists of 1.5 times 1.1 for the gamma F3. And well, this is for load combination type 1 is ultimate limit state. So, but when you look at the HA and HB45 auto cases, it's only appear 1.1. So what does it mean? It's because the factors of 1.3 for HB, the partial loading factor 1.3 for HA and HB loads at ultimate limit state is already inherently created within the HA and HB45 outer load, which you already defined through the moving case earlier on. So it will not be repeated over here, otherwise it will be double counting. So over here we just show 1.1. Actually the 1.3 factors is already hidden within this load case before. So this is the things that we need to know, this difference between auto and non-auto. So I think it's still the end of the presentation by today. I don't know whether I overshoot the time, but just about the correct time. So it's still 10 minutes to go. It's open to Q&A session at the moment. So if you have any question to ask me, then you can raise your hands and type. I will try to answer as my very best. Yeah, so and still waiting for questions. So same time. So can see any question come out or not? The PDF file for the presentation slide, yeah, I think it's possible. MIDAS Civil will, the technical team will send you the PDF file. This is to answer the question of, let me see, it's too many of them. Oh, this another question from Vijay from India. So the question will be, is there any option to model the fully integral bridge using the wizards? Superstructure integral with RC apartments and PAUs. Well, the PSC wizard just demonstrate just now is only able to model the simply supported bridges. It's not for the integral bridges. There will be another wizard to model the fully integral bridges, or you can just modify the modify the model has been created by using the PSC wizard and by modifying it, to incorporate the PAUs, your apartments into the models. Yeah. Then let me see who else the questions. Very hard to see the question over here actually. Well, who's the patient again? Let me see. Very hard to see the patient. I think that you can just email the question to us, and then we will answer you through the email after the seminars. As for me, over here is really hard to read out the questions. It's all jammed out into more tiny space over here. Yeah. Can't see the question honestly. Yeah. Anyway, for those questions, I think you can email to the organizer so we can try our best to answer the questions one by one. As it's really hard for me to see the question over here. Can't really see it. Yeah. We're sorry about that. Try to figure it out still. Can't see the patient. All right, someone is requesting for the PPT file. I think it should be able to give you the PDF versions. Yes. This is very hard to see. Yeah, I think, sorry about that, because I think we really can't see the question over here. It's very hard to see.
Hello, Chang. There's a button to enlarge the question dialog, actually. Next to
wait. Next to X.
Yeah.
How do I enlarge it? No. Oh, yeah. Okay. All right. I managed to, sorry about this. A lot of questions. So I have to go one by one from the beginnings. Which ones? Yeah, first one from Jiong Lao. Jiong Lao. Well, the slide will be shared. I think the organizer will issue the slide to you, I believe. It's meant to be shared to all the attendees. And how reliable is this software compared to others? Well, I can tell it's very reliable. That's I've been using it for years, and I found it's very powerful and very reliable software. Yeah. And another one from Yu Ki Chong. Okay, it should be Chong Yu Ki actually. Is SB20 going to govern the design? Well, I would say is for the long span bridges. For example, you have more than 40 meters plus 50 meters per span. SB20 we usually governs because SB20 loading is being configured to a series of trailer more than 10 meters. It could be up to 30 meters and long. So for long span bridges, yes, SB20 will be governing that. But for short span, HP is the governing. Let me see the question. I already answered VJ questions. Yeah, questions. Okay, this is from Titus Core. Thank you for the presentations. Why only model the columns and piles as master and slave without modeling the actual pile cap with piles with springs? Let me see. Without modeling the actual pile cap with pile and spring. Well, usually we will use another software to actually model the pile group stiffness because it's much straightforward and easy way to model a single point spring stiffness rather than we model the actual piles with the subject reaction spring along the piles. That would take a lot of time and effort also. And then if you are having a non-preceding piles, it's accurate enough for you to model the pile groups instead of the model in every single pile out. Because if you want to change, for example, change the numbers of piles or the spacing of the piles, then you have to remodel the whole pile elements again. So it's going to be time consuming. So it's always accurate enough to just do a single point spring, and then just model the springs and at the bottom of the pile cap. So you can do that with actual pile cap and also pile spring, but it's going to be time consuming. So the question from from Telwit Chai Ku Sirawet. Sorry if I can pronounce your name correctly. Sorry if you already talked about this, but I want to ask if it's necessary or not to input prestressing tendon in the analysis model, because we usually design it later after we got the results. Well, is the designer preference if you not model the prestressing tendon in your analysis, because you talk about the global model, you need to model in the prestressing tendon in your analysis, because the prestressing tendon prestressing effect will give the external some kind of loading effect to your movement of the end of the deck, and also to the some pier column forces. So by doing so, you actually can capture the effect of prestressing, just like secondary tendons effects to your multiple span bridge. So I think you need to model the prestressing tendon in the analysis to be correctly capture all these loading effects. Well, of course, you can always check the prestressing design outside the model manually. That's the designer choice actually. Yeah. Second question from some David also. Also, if my bridge is in determinate structure, that wouldn't make any difference, right? Yes. If you have a single span bridges, it will not make any difference to whether you have model in the prestressed tendon or not. You just not. If you have a continuous two spans bridges, especially you have continuous structure, then the intermediate determinate structure, then the tendon effect will come into play. The secondary prestressing effect will come into play. Then a question from Wong Siu Kian. If I create the Liveload combination by myself, not the auto-generated HB45 auto, when I put in the factors, shall it be 1.1 times 1.1 or just 1.1? You have to consider the gamma F3 of 1.1. Yeah, in your model, in your log combinations. So yeah, it's strongly recommended you have to input the production between the 1.1 times the partial log vector together. For example, you have 1.1 vectors for the 1.1 for the partial log vectors. You have to times the gamma F3 of 1.1 again to produce 1.25. Then you have to input 1.25 in the log combinations. Sorry, 1.21. Yeah. Okay. I cannot go through again. Question. A question from Rush Hoover End. Hi, can we combine all model with SP vehicle as per the CS456 code block explanation? Sorry, I'm not familiar with the CS456 code block combinations. Really is not familiar with it, so perhaps I cannot answer the question about it. Another question for Osbu Mood. Hi, Chong. Yeah, is there any continuation for this webinar, including analysis and design after the wizard input? Yes, the part 2 will be coming out next week. I think it's on next Thursday as well, 23, not mistaken, same time. Then another presenter will come up with the more details tutorial on this. Then that seminar, we talk about the analysis and also design after the wizard input. Yeah. Just sign in on that one. I think it's time now. It's 3 minutes after 3 o'clock already. So for those questions that's not managed to answer, so please feel free to email to us, and we will actually try to reply to you one by one. So yeah, thanks for attending to this seminars. We will see you soon in the next futures, perhaps. Yeah. So by then, goodbye, everyone. Thank you for your time. Yeah. Bye bye.